constant velocity. In this video, we'll be going over a brief introduction on this lab, the analysis of our experimental object, the ping pong ball, the construction of the computational model, a comparison between the observed and predicted graphs, and finally a what if, what does it mean conclusion. To begin, the purpose of this lab is to compare the observed position of an object traveling at a constant velocity, which we will obtain by using tracker, to the predicted position calculated from a computer-generated model by using GlowScript. The main goal of this experiment is to help demonstrate the principles of Newton's first and second law of motion. The first states that an object in rest or in motion will stay in rest or motion unless acted upon by an outside force. And the second states that the motion of an object is directly proportional to the magnitude of any of the forces applied to it. We also know that an object is in constant velocity when it has the same speed, goes in the same direction, and has a net force of 0. Our system in this case will be the ping pong ball, and the surrounding will be everything else in the kitchen. Now for the results of this experiment, we will predict that the ball will move at a constant velocity to the right. The formulas we'll be using is the velocity update formula, which is just the net external force being equaled to the change in momentum of a system divided by the time over which it changes. Now, if we take it further and derive it, we should get that the final velocity equals the initial velocity plus F net over mass times the change in time. This tells us that if the F net acting on our system is 0, then the velocity does not change. The second formula is the position update formula to further show that the final position is going to be equal to the initial position plus the final velocity times the change in time. In this case, the final velocity is going to be equal to the initial velocity. After understanding the applications of these fundamental principles, here are the steps I took after to complete this lab. So here's the video I took of the ping pong ball going at a constant velocity put into tracker. The little dots following the ball is just the center of mass inputs that I had manually entered in at each time frame. And we can see that I had a total of 40 data points. Now looking at the position versus time graph, we can see that it appeared to be linear. However, we're going to make a computational model to show if it really is linear or not. From the data we collected from tracker, we can see that the total time it took from the ping pong ball to go from start to finish was about 0.667 seconds. And the initial position was 0 meters from the X, Y, and Z positions. And the initial velocity can be calculated by taking the change in position over the change in time of the first two time frames, which will give us 1.86 meters per second in the X direction. These three data points will later be used into our computational model. Now, onto our code, I first added that the net force is 0 because constant velocity means no net force. Then I inputted the initial velocity and the initial position given from the tracker analysis we did on the last slide. Next, I set delta t to 0.017 since it was just the time interval between two measurements. And the mass of the ball doesn't really matter in this case because it does not affect the velocity. This is because in the velocity update formula, it states that if the net force is 0, mass just cancels out. And then finally, the position update formula just predicts the location, and since our velocity is constant, we should see a positive slope in our position versus time graph. Here is what I see when I ran the code in GlowScript. Now, after finding our observed and predicted data points from our tracker analysis and the computational model made by GlowScript, we get this graph on the right, which basically tells us that as time goes on, our experimental or observed positions start to diverge away from the predicted or theoretical position, meaning that there must have been some outside force that slowed down our ping pong ball. Some possible errors that might have occurred includes friction, air resistance, and position tracking, which is differences in placing the center of mass in our tracker analysis. Now, to conclude, if the axes were changed or flipped, nothing would happen except our slope would now be negative. The physics of it all will still stay the same. And since our computational model overestimated the position of the ball at greater time intervals, there had to be some other resistive forces at play that did not give the system a net force of 0. And this ends my first lab. Thank you!